Oh, nice. Okay, shall we get started? I hope people can hear. So welcome to the final class of CSE 242 Machine Learning. I hope you've enjoyed it so far and you've learned some exciting new things about machine learning. And of course, this is not everything like we've done in this class. There's much more you can do in machine learning, much more. By taking follow-up courses as well. We'll talk a bit more at the end of the class, but I hope it was a good experience for everyone so far. And so in this final lecture, we're just going to talk about some more, let's say, more recent, very recent neural network models. And this is more like, these are kinds of like techniques that emerged just in the last 5 years, 6 years. Some are from 2014, but these are all quite new techniques. Like we'll talk about autoencoders. So, but let's remember what we were discussing about last time. So last time we were saying how we can put together a neural network. So look at this diagram. We can put together a neural network by combining many layers, which use convolutions. Remember what a convolution was doing, was applying this filter on sorry, I had the slide here, this one. It was putting together a filter and sliding it over the entire image. That's what a convolution was doing. So we're putting together many of these convolutional layers into a neural network, and then also alternate with max pooling and so on. And at the end, for example, we have a fully connected layer that predicts the output of, for example, whether this image contains a digit and what digit it contains. So there's 10 neurons we have at the end there, which each neuron would correspond to one digit 1, digit 2, up to digit 10. And this is what we were, and this is how we put everything together in this neural network. So let's I think we stopped here, and then we went on that demo. So the question that became quite sort of like debatable from 2009 up until 2012 was whether like deep architectures are important. Like, for example, by deep we mean having many layers, and it seemed that the answer has been yes, at least given the last few breakthroughs in the last few years. So for example, these are the results on this ImageNet competition. The ImageNet is one of the most famous competitions for object classification in images. So you have many categories. For example, cats, dogs, airplanes, chairs, all kinds of objects, all kinds of animals, and you have to predict which one of those categories is shown in a picture. For example, does the picture contain a horse? Does it contain an airplane? Does it contain a person? All kinds of things. So it had around more than 1,000 different categories. So it was a lot, quite a complex task. We humans can do it very easily, but for computers it's difficult. So it seemed that the pattern we saw seems to be that over the years we kept adding more and more layers, for example, and these results kept getting better and better. This was the pattern that we saw. So and And also this also scale with much more data. The more data we added, the better. Like, you know, millions of images, we're going to tens of millions, hundreds of millions. The results keep getting better and better. And there is also this universality theorem that was published by Sibenko in 1989, and it's also called the universal approximators theorem. So basically what it tells us is that the neural networks can be universal approximators. They can arbitrarily well approximate of any arbitrary function. So and this even holds for apparently for shallow networks under some conditions, of course. We're not going into details of the conditions, but under some conditions, neural networks can be universal approximators of the true function. This is the key takeaway. So there's and today we're going to talk a bit about some more specific architectures. For example, we talk about like generative models, about variational autoencoders, generative adversarial networks, and so on. There's many types of more specific specialized architectures that can do certain tasks. For example, there's networks that can process sequences. For example, like a text, it's a sequence of letters over time, or audio sequences or video sequences, and those, for example, are more, for example, use what are called recurrent architectures, recurrent neural networks, or for example, in particular, the long short-term memory type of networks, which use skip connections, are types of examples that are more specialized for these kinds of tasks. So, and there's also some drawbacks we have to, of course, probably discuss a bit about data and compute time. These kinds of networks and models require a lot of data, tons of data. They require tons of compute time. And nowadays, for the state-of-the-art models, it's only actually companies that can afford to train. It costs millions of dollars to train some of these networks. And for example, you need a lot of resources, for example, to train all these state-of-the-art models. So we need a lot of data, a lot of compute. There's also issues about interpretability. When you have these very large networks, how do you understand what it learned? And I think Leilani in her talk hinted a bit at interpretability of how do you understand that? How do you make sure the model is robust? How do you put safety checks on it? So let's discuss a bit. So the autoencoder. What is this idea of autoencoders? So imagine you have images of cats, of dogs, of so on, and what you want, the key idea in the autoencoder is that you want to have a compressed representation, a compressed code. So basically, you don't want to, for example, there is a lot of redundancy in the image. Maybe adjacent pixels here that are close to each other have very similar values, similar RGB values. So maybe which tells us there's a way to compress it as a result. So the autoencoders basically pass the image through a neural network encoder, and it gives us a code that is then passed through a neural network decoder to retrieve back the image. And there's a loss function that is implemented between the input image and the output image to make them to be as close as possible. We want these images to be as close as possible. So if it generates a cat, if it starts with a cat image, it generates a dog image. That's not good. We want them to be much closer, so it would enforce a loss. In particular, the code is much lower dimensional. So often how people represent these models is more like this. So basically, this is the bottleneck layer. Essentially, this is where this code is. It's much smaller. It's, for example, let's say it has 100 dimensions, whereas the image has 1,000 by 1,000, 1,000,000 dimensions. So this could be like 1,000,000 dimensions. This could be just 100. It's a very compressed code. So that's why it's represented like that as a trapezoidal sort of shape. By forcing it to go to that bottleneck layer, you essentially compressing the information. And then the nice thing about these approaches is that then when we take a new code, for example, we can sample a new code from that space of codes, also called like latent vectors. These are also called latent vectors, by the way. We can sample a new latent vector, and then we pass it through the decoder network, and we generate a new image. And that's how we can interpolate between two different images, by interpolating in these latent codes or latent vectors. Any questions so far? No? Okay. So same idea here. Why I've added extra here in this slide is that the cost function is for all the data points 1 to n. We do, for example, a sum of squared differences. For example, now we do the differences between the input image and the predicted image. So this is the input, this is the output or the prediction, and then we try to make them as close as possible. And this is the loss function is always it's called the reconstruction loss. It's also called the reconstructed image. So it's trying to match the reconstructed image as close as possible to the input. Yes, so, and in particular, there's this idea of what is called the variational autoencoder. So far we've only spoken about autoencoders. These are this idea of the autoencoders. We just passed it through a bottleneck layer. A variational autoencoder, so with the variational base, this has been like a very, very powerful technique that was published in 2014. And so around 8 years ago, and the idea is that when you put the input through the encoder, you don't get one single code here. You don't get one single vector. You get a distribution of vectors. Yeah, a distribution of vectors now. So, and the distribution is captured by a Gaussian distribution, so which will have a mean of m. Think of it as a vector m, which has elements m1, m2, m3. Some sigmas, sigma 1, sigma 2, so again a sigma vector, and also like and this also is a noise vector. So basically the idea is that if we can sample from this distribution afterwards by literally sampling 0, 1 noise. These epsilon vectors are so essentially epsilon is sampled from n 0, 1. A normal distribution with mean 0 standard deviation 1. So these are epsilons e, and then we just multiply them. We multiply the noise vector by the standard deviation and add the mean, and that's how we sample. We basically this ends up that our C there will then be sampled from n of mean m and standard deviation s sigma. The key idea, the reason why this had to be done like that, was because it's not possible to flow gradients with backpropagation through stochastic inputs. But you can do this trick where you basically have these vectors fixed, and this is noise that is sampled. You don't flow gradients through here anymore. You just flow gradients through these m's and me's and sigmas, and this works. So you can flow gradients in this way instead of sampling directly from n or from a mean normal distribution with mean m and sigma. Yeah. So again, we minimize the reconstruction error in this case. So again, the main difference now is that we learn a distribution of codes here. We just don't learn one single code. We learn a whole distribution. Can also be seen like this. So again, a mean vector and standard deviation vector, and then we sample the latent, and then we pass it through the decoder, and then we get the image or even yeah. There's another very popular technique that was published by Ian Goodfellow and by his advisor, I forgot, Joshua Bengio, in 2014, and this is called the general adversarial networks. And general adversarial networks, or GANs, what they do is that they, we have two different networks. One is a generator, one is a discriminator, and they play a game with each other. They're trained against each other. And this is a very powerful technique that was used to generate images, videos, simple conversations, any kind of higher dimensional data you can use to generate. You can use these models to generate any kind of high dimensional data. It can be anything. Can be visual data, could be audio data, and so on. Text, all kinds of things. And this idea that we have two models, and they are sort of evolving with each other, co-evolving with each other, or competing with each other, playing against each other, and you can phrase it as you like. This idea is actually very powerful and can actually have far-reaching implications. And we see it a lot also in, even with us, with humans. We have kids playing with each other, so like, sometimes, and they learn from each other this way. And by doing this kind of game, like two kids playing with each other, then they learn new tasks, and so on. So it's something that we humans do as well. So we can do this in models, with machine learning models. And this actually has been used particularly well by AlphaZero, which was the model from Google, DeepMind, that was used to win against the world champion of Go. So, and AlphaZero, how it was trained is that basically they had two models that were playing the game against each other. And they were training them like that, basically. So they were playing the Go game, the game of Go, and you can think the same you can do with chess, any board game. You can have them play against each other, and then they improve over time. And if you run them, let them run many days, for example, let them learn, and they will learn to play very well. So this way you don't need to have even a human to play with the AI model so that the AI model can learn. The AI models can play against one another. So this also goes a bit into game theory. So some of you are more mathematically inclined. There's there's courses also on that. Like there's a lot of literature that was published on game theory and how players can play these games, and there's this code of equilibria that emerged called Nash equilibria and so on. So yeah, there's a lot that we're not going to cover that in the course. How do we learn a GAN model, a generative adversarial network? How many of you have seen this before, just to get an idea? Okay, so quite a few, but not everyone. So we have two networks. One of them, one is a generator network. One of them is a discriminator network, and they basically try to play against each other, try to kind of fool each other. How it works is that for example, we randomly sample a vector, we pass it to the generator network. For example, this generator network is trying to produce a digit, the image of a digit. But let's say initially it doesn't work that well. So for example, it produces this kind of much blurrier image which is a blurry 0. The discriminator network has the task for it is to tell whether the image was fake or real. So in this case, the discriminator thinks, oh, this is not a real image. This is a fake image that was generated by the generator. So I'm going to give it a probability of only 0.13 of it being real. So very low probability of it being real. But then what we do is that we update the generator. We keep improving the generator. And let's assume for now this is fixed. The discriminator is fixed. And we keep improving the generator up until so we do a version v2, for example, up until it starts producing better images, like this one. So now it starts producing much more realistic images. And then the discriminator will think, oh, this looks like a real image. It's not a fake image anymore. So it will think, oh, it will assign it a probability of 1 of it being real. So, and this is how we improve, for example, the generator. And we do the same thing with the discriminator afterwards. Then afterwards, for example, we fix the generator and we improve the discriminator. And we keep going back and forth. And how we update them was with backpropagation and stochastic gradient descent. So we've seen in last lecture how we compute it with backpropagation. We can compute the gradients of the loss function with respect to the parameters of the weight of the network. So that's the backpropagation. And then the stochastic gradient descent is just telling us how we use that gradient to take steps in a direction that minimizes the loss function. And we use some stochasticity. So. And the stochasticity in particular is given by the fact that we don't load all the images at once. We load them in batches. And this gives us a stochastic effect. And that's why it's called stochastic gradient descent. Because we don't load all the data set at once. So So the model can also be seen be shown in this way. For example, so we on the left hand side we have the discriminator flow. So for example, we can sample the data from the training data. We pass it to the discriminator, and the discriminator tries to predict whether it's fake or real. And discriminator again is a differentiable function. And on the right hand side we pass, for example, we generate a new image from with the generator. So you generate some input noise. We pass it through the generator model G. Then we pass it to the discriminator D, and so on. And then they try to optimize this game. So this is the loss function, for example, for the GAN models. So you can understand this by studying. So if you follow me, So just look for now. Just look at here at this X. This is the input image. This is an image that is sampled from our data set. So we pass it to the discriminator D. So we pass it through the discriminator model D, and tells us the probability of the probability of it being real or fake. We take the log probability of that, and we take the expectation over all the data sets. We do the same for all the images in our data set. And then what we also do is that we also sample latent sample vector Z from the latent space of the generator, and then we pass it through D, and then we optimize this other function, which is the log 1 minus the D of that, because we have to flip the sign of it. And we take many, and with this expectation we take many samples of Z. That's what it means. We take many samples of Z, and therefore we. Any questions here? So if I do a small diagram on the blackboard, initially what we had with the autoencoder was that we had some input image. It was passed to the encoder. This is called the encoder. This is called the decoder. Encoder network, decoder network. And here we had a loss function. So, and here we had an image, but we also had another training image. And we overlap them each other, and then we compute a loss function like that. This is what we had previously. What we have now with the GAN models. Can you all see here? Yeah. What we have now with the GAN models is that we have a latent vector here, Z. We pass this through a decoder right away. And so this is the this is called the generated model G. This is the generated model G. And then we pass it through the discriminated model. So the discriminated model would also look like this. And this is D. And here it predicts, it's just a single variable that predicts whether this is fake or real. So this is fake, real. So look, so we start from Z, we get a large image, like a full-fledged image, and then we pass it through D. This is flipped. We start from a full image, then we get a vector, and then back we decode it. And of course we also pass. We have a separate pipeline where we basically also pass like training images. And we can also pass these as input here. Instead of passing the decoder, we pass this like these training images instead of passing generated images. I hope you can see it over there. So it has been used in many tasks. For example, it has been used in video to do the next frame prediction. So, for example, if we have a video of a human head, for example, and the task is to predict the next frames, what are the next future frames, For example, if you use something like a mean squared error loss, you get blurry results. But if you use these adversarial losses that are used given by GANs, by generative adversarial networks, then we get much sharper images that they're not trying to blur out the detail and try to average things together. And this is much closer. This is much closer to ground truth than having this blurred result. And the reason why the blurring happens, actually, any question for everyone: why do you think the blurriness happens when you do use a mean squared error loss? Any ideas?
Some sort of error, that's why they cause blur in it. But that's my wild
Any other ideas?
So I can't think of from MSC side. I can think of from L1 loss, where we can take direct difference of pixels. Then it's like we are kind of making it very hard constraint over the pixels. It should be the same in L1 loss. But I'm not sure about the MSC.
About the loss function, MSC, I don't remember saying about my images with blurs. Just pretty much a loose function. Like where he said, maybe there's some type of unknown space, type of margin error.
Let me tell you. So. Our current understanding of why this happens is because so the task is inherently, so you have a series of images. So this is like an image with the face. That image with the face, and we have and it's a video. So you have a series of the same images, and at some point it stops, and then the task is to put in the next frames, right? This is what this is about. This is the setting. So then. There are many possibilities. So I'm just going to do so one possibility is to kind of the head might turn to the left, might turn to the right. There's many future possibilities of how the head could move. So there could be many different possibilities. And these, and more precisely, these kind of future possibilities essentially lie on what is called a manifold of a possibility of images. So it's kind of it's a subspace of the high dimensional space. This subspace of possible frames into the future. So the entire possible space is what? Is like the number of pixels you have. It's for example, it's a space. If you have 1 million pixels in the image, then that's 1 million dimensional space. And that's only for grayscale images. Out of all those possibilities, there's only a subset of points in that 1 million dimensional subspace that can give us reasonable future frames for this particular task, and that's called a manifold. And it's more, so you'll learn this more if you take more advanced machine learning techniques. But essentially, what the MSC loss is doing is that it's taking an average in pixel-wise space. So this is the MSC solution. This is the mean squared error, because it's minimizing the Euclidean distance between.
So it's like taking all these images that are reasonable and then averaging across them, and potentially coming up with something that's no longer reasonable.
That's not going to. It's like if you ever try to average together multiple images roughly the same, then it starts getting blurry essentially, because it's trying to take an average. So it doesn't know which one of these it has to choose. Any of these are possible.
It tries to get all of them.
Yeah, it's trying to get all of them, but it would be much better off if it would take Just one of them, yes, yes. So let me do.
Example when you need to add the images and divide them together.
Yeah.
Are you guys using what type of this type of probability of good images and blurry images?
Yeah. I'll get back to that. I'll give you another example. But yes. I know what I mean. So this is the manifold. Let's say this is the manifold. It's like it's a subspace of the it's a subspace of solutions of all the images that could be future frames potentially, and whatever is outside this manifold is not a solution. It's a blurry image. It's an image with noise or anything that is not sort of good. So by taking the average of around all of these, you're much worse off than taking any point on this manifold. If you have taken this one, this would have been a solution, or this one, or this one. But because you're taking the Euclidean distance in pixel space, you are essentially getting a blurry result. So that's why you get blurry results with MSE, with mean squared error. Yes?
So is this in case of videos when we are predicting next?
Yeah, yes. This is what I was trying to say. So frame. So this is frame 1, frame 2. And this is, afterwards, frame 4 or even frame 100. So anything.
But it might get blurry because when we take the mean square error, all of the pixel values change at once rather than what actually happens in images where only a section of them change.
You thought the image would get blurry because all the
All
pixels
of them change simultaneously.
change simultaneously.
So it is difficult for it to render that frame and it gets blurry.
But there should be ways in which indeed all the pixels change simultaneously, but you want a good result. You want one, and there's many results that you kind of like as we were saying, there are many possibilities of how.
So when we take average, all of the values will change by some.
All of them will be averaged out. You average out all the solutions, essentially.
I thought it's just there are too many pixels to change at once, so that's why the image might look blurry to us.
But yes, but you can solve that by having a good model. With a good model, you should be able to solve that, like a powerful model that learns how to change all the pixels at once. Yeah. So you asked for another example of that. So what another example? Does it make sense? Why there's this idea of how many of you understand why kind of like this averaging across? Does this make sense? Yeah. Imagine. So here's another example that I can give, because I think it's a good one for interpolation. Let me do it here. Imagine you have a series of images with a happy face. So here you have a happy face, here you have a sad face, and here you have like a neutral face. So what I'm hinting here is that there's a dimensionality over there's a latent dimension over the sort of like the mood, how happy or frown, kind of going from all the way from happy to sad, for example. So if you then try, in theory, if you wanted to take one image from here, x1, and this one x2, and average them together, you would actually want sometimes to get a neutral face, right? Because you want to average out the two, let's say, sort of like emotional states, for example. But what you instead get, if you do it in pixel-wise loss, you get like a blurry image, because essentially that's what you instead get is you don't get like an image with a neutral face. You actually get a blurry image, which looks kind of strange.
Is there a way to modify it so that it would get kind of that neutral face?
Yes. You do it in.
To quantify all these images such that one is considered an average.
Yeah. So you do this in the latent space vector z here. You represent all of them in latent space, and you do the averaging in z's. So then, you do an averaging in latent space in the latent codes. So then when, instead of working with the images, you work with, so you'll get like a z1 corresponding to x1, and you get a z2. And then you do the averaging, z1 plus z2 divided by 2. And this is an average vector, latent vector, and then you pass that through the generator function g. And that will give you then
So that should give you
a phase that is neutral.
between these two,
Yes.
but hasn't blurred.
Yes, yes, yes. So this would be like, you know, a clear image, whereas if you do it in image space, x1 plus x2 and a half of that, this would be blurry. Does that make sense? So it is another reason why these kinds of interpolations are another reason why these images, these models are very powerful. You can, in this latent space, you can do a lot of things here in this latent code here we're showing earlier. This is that code I was talking about. You do the averaging, that interpolation in that space, and then when you pass it into a decoder or through the G, then it works. So they have also been used. These models have also been used for super resolution. So, for example, you are given a low resolution image, and you try to get a high resolution version of it. For example, maybe your camera was blurry and so on. So you can also use these models for that. So this is another work by Ledig in 2016 that we're showing how you can use GANs, and so this was the original image, but then it was very much downsized essentially. So then like the task was to come back and if you do a bicubic, a standard bicubic super resolution, I don't know if you can see, it's much more blurry this version than the other two, and these ones use GAN, neural network models. Also, image-to-image translation are very powerful tasks again, where these models can do very well. So, for example, the idea is you have a hand drawing of a purse, for example, and the model can take those kind of guidelines from the hand drawing and actually draw the full object with texture and everything. And the same for here. They can also do, for example, like they can go from a segmentation to an actual image, for example. So this is a segmentation of cars, of the street, and so on, so where you label each pixel with a class, and you can generate a full image. Or you can go from like satellite images to, you cannot see, but in general, I know this paper, it was basically Google Maps. So it's it was basically you have a satellite, and you can generate how like the Google Maps sort of like street view, like sort of like type of image. They can also be used to generate just like images from scratch. So with deep fakes, I'm sure many of you have seen. So you can generate. So here, this is an example with the bedrooms, trying to generate bedrooms. But this is again older work. They've gone way better by now. They can generate highly realistic bedrooms. You can do vector arithmetic, which is absolutely fascinating with these models. So for example, if you have a vector that represents a z vector. This is again, we're talking about the latent vectors, z here, that would generate this image of a man with glasses. You subtract the vector that represents the concept of a man, and you add the vector that represents the concept of a woman. You basically get a woman with glasses, basically. So you get, because you subtract the difference between this and that, these two, is that this one has glass and this one doesn't. So then you can add glasses to an image, to a person, for example, just like that.
That top left one looks like a woman with two black eyes.
Yes. I know. This is again, this is all the work. They've gotten way better now. They look quite realistic now. So this is again from 7 years ago, but the field moves so fast that again it's incredible. And I've seen some examples. They look very realistic. Like
how do you include the vector space after I just want to know because if people create like 3D figures, like in anime in Japan, they create like characters and animes and like I just want to know.
What's the question?
Like how you can use like 3D, like use the vector space thing. You can create like 3D image character. I think that's
how do you use the vector space thing to create a 3D character?
And then
like a 3D image, you mean?
Yeah, 3D.
From 2D? Yeah, so you're talking about a 2D to 3D reconstruction.
Yeah.
You can do that. Actually, there's a very active research field, and especially like it's used a lot. I'll mention a bit about it, like even later on. You can use these kind of models to do that. And actually, I have some projects even right now, research projects in which we do exactly that. Like we have a single slice of a brain scan. We try to reconstruct a full brain image, for example, a 3D brain image. We try to infer what could be the 3D reconstruction from a single slice, from a single 2D slice. So that's one way, for example, in which we're doing that. There's also some other kind of models. For example, this is an example of what's called a plug-and-play generative network. And basically, here what they do is that the model was trained to generate unconditional samples of points, but then you attach a separate network that says that somehow tunes in and says, oh, I just want you to. For example, this network tells us I only care about dogs. So then basically your generative network then becomes conditioned on only generating dog images, for example. Or you append a separate kind of component which only to say I only want to generate cats, so then you generate cats instead. But this way you have a universal generative model, and then you can plug an auxiliary component that conditions it on only a particular class. So that's another thing people have done. Just wanted to clarify, does this make sense? I'm going a bit back one slide. Did this make sense of how do we get this vector of a man in general? How do we get it? Or a woman, or any big class. We only have a data set. So yeah.
We'd be training off data that we hopefully have classified already.
Yeah. So we have many images of a man, women, like all kinds of categories, dogs, cats, or whatever we want. So, but how do we get like a single vector for the entire class, though? It's like a representative. How do we get a representative image? I suppose that's the question.
So, like when we start with that Z, right, in the generator network.
Yeah.
So let's say it generates an image, some random image. We try to get the difference of this or the representation of data set with that generated image, and we try to move the gradients in a way that it manipulates Z so that we get the representation of that class, whole class.
Yeah, but how do we get a universal kind of like data point for everyone that represents, like, let's say. Let me show you. So, so we would do. So, for example, if we plot the latent space for our data set. So, for example, let's say we just plot 2 dimensions. Can you all see here this plot? So here this is Z1, this is Z2. Let's say Z is 2-dimensional, but it can have like 100 dimensions and so on. So we would have like some points here with like, like let's say man, some other points with women, for example. They could overlap. Could be a lot of overlap. But what we do is then basically and I don't have other colors, but we essentially find the mean vector. For example, we do an average for this particular class. So for example, this point here would be the average across all the for all the women categories, and this would be like an average of all the main sort of, for example, like data points, and that these vectors here would be the ones that kind of like like for example like summarize, like for example is an average of the entire class.
Couldn't those
So
vectors run the risk we mentioned earlier of being blurry?
say that again. Yeah, no, because you do this in latent space.
You do it in the latent space.
That's the key thing. Yes, this is what we were saying with that, with those. Yeah, you do the averaging. If you do it in latent space, then you just pass it through. Yeah, these are the latents of each data point in your class. So then what you do when you do, for example, like, and you also have a subclass here. For example, these would be the man with glasses, and you have another vector here, another mean for that. So then you subtract this vector, this distance, and you get this kind of vector. And then you add this other vector, for example. So then you, this way you subtract that difference, which was sort of like, like essentially this operation going from here to here, it's as if you remove glasses or add glasses. You can think of it like that, this going from here to here. Because this is an average man, this is an average man with glasses. So going from one to the other, it's like you add glasses, basically.
How
Think of it like that.
Does this maybe work on like, what if you had like man with glasses and you wanted to produce a cat with glasses? Because I mean, a man and woman have a lot of similarities between those two.
It doesn't always work because of the disentanglement problem is called. Essentially, sometimes you cannot easily disentangle the concept of glasses from the rest. You're trying to separate it, like having glasses.
That's why we have an image here, a woman that looks like
Exactly. So it hasn't learned it properly. But in general, like if you disentangle the concept properly, then it would learn just the concept of glasses from this, and then it can apply them. It should be able to generalize to any other things. Like for example, you can even apply it to a mannequin. For example, you can add glasses or anything, absolutely anything. Even a spider, I guess. All kinds of and that's the generalization property afterwards. It has to be able to generalize to new concepts. It's not an easy task. It's really not an easy task. But these are kinds of things people are trying to do. For example, and it's important, especially for photo editing, for creative works, for example, for movie studios, for example, for creating special effects in movies, all kinds of stuff. For example, you have an actor, they need to have they had an accident, they have to have a scar on their face. You just do this kind of like, semantic editing in this latent space, and then you have the normal image of the actor, but then you add automatically the scar on their face. So then you will keep doing that. So these are super useful for these kinds of applications. And another key task that people are trying to do, for example, is image captioning. So the idea is you have a picture, a picture, and then you try to predict to generate a text that describes that image. And this is the image captioning. And sorry, actually, this particular slide is referring to the other task. So you can do the other task as well. So from the text, you can generate images. You give them a snippet of text, and you can generate, we want oranges on a table next to a liquor bottle, and generate images with the oranges next to a liquor bottle. I think it's fascinating. Again, we can do these kinds of stuff these days, and even much better than this example. This is again from 2016. There's really good models nowadays that can do it really good. And in general, there's other kinds of models apart from autoencoders and the GAN models. There's other, for example, models called like conditional flow models. There's flow models. There's autoregressive models. There's, for example, there's diffusion models. And the key idea there is that they try to have losses between distributions. Like essentially, you this is your true data distribution. These are all your, for example, like your training points. These are all your images. One image is another image. These points are all different images. They have a distribution, and they try to match your generated distribution with that true data distribution. And this is what they're trying to do. And you have a loss function between these distributions. And this is a loss on distributions. I'm really emphasizing this. There's not a loss on individual data points now. This loss goes across the entire distribution. So if these two curves don't overlap that well, then they will have like a high loss. Otherwise, if they overlap, they'll have a low loss. You see, they're not exactly the same in this example, but it is trying to, the generative model is trying to get as close as possible.
The loss is just the difference between the two, right?
Yeah, but again, in distributions, it's not in the individual data points anymore. It's a distributional loss, and sometimes these kinds of distribution losses, there's an example of it is called the KL divergence, the Kuhl-Black-Leiber divergence, and it tries to, and it's based on entropy, sort of like fundamentals. There's another kind of distributional loss that is quite popular called the Wasserstein loss, which we haven't studied, for example, or it's also called the Earth mover, and there's many other kinds of losses that you can do over the distributions. And another very powerful and very interesting application of deep learning was for reinforcement learning, what we were studying just a couple lectures ago. So we can do Q-learning using deep learning. So if you remember, in a reinforcement learning, we had an agent, was in a particular state. It was trying to learn a policy over Q states. We had a state S and an action A, and this was giving us a Q state, Q of S and A. And then we were taking an action in the environment, would take you to a new state, it would give you a reward, and so on. So we go all in a loop. The key difference now is that we're trying to learn these Q states with a deep neural network. This is what deep Q learning is. We're trying to predict the Q states, to do that Q iteration, Q learning, with a deep neural network. So we have a deep, for example, a feed-forward neural network from a given state that predicts the Q states for every state and action. I remember the Q states, it was something like for every state and an action pair. It's kind of like telling us what's the discounted future reward into the futures, like how many, what kind of reward they're going to get now, and then discounted later, and discounted even some more steps in the future, and so on. So the Q state is kind of like summing up together, and we can predict that with deep neural net. And how it works is, again, we're trying to approximate the Q state over S and A with this Q hat, which is a neural network that predicts Q of S and A that is parameterized by weights theta. So here theta are the weights of the network that we're trying to learn the Q states. And we have the same equation for Ballot propagation. You've seen this before. Nothing has changed here. And afterwards, what we do here, so in this line, if you look here, we have, how we compute the loss is by taking the current rewards that we observe, and we discount when we subtract the predicted Q state by the network, and we do squared errors. So actually, and it's not actually, so why? So it was not the current reward; it's actually the expected value of the current reward plus the discounted Q state into the future. So this again, the predicted Q state. We take the maximum, we discount it by gamma, and we add with the current reward, and we take the expected value over all the states that we can land into, states S prime we can potentially land into, and this is out of our control. Even if we take an action, the environment can land us into a new state, into different states.
What's y sub I above that real quick?
What's what?
Y of I, in what you were just looking at.
Here.
Yeah.
Yeah, it's like, forget about this for now. It's the current reward plus discounted Q value into the predicted Q value into the future, and actually, but using the parameters from the previous iteration. It's a loop. We're trying to train the network. That's why we're doing iterations over the parameters. But we're also trying to learn learn the environment. So we're trying to essentially, you see, we are using these. We are using the predictions from the previous iteration to get a value of the expected future reward, and then we're using it to compute a loss function between the current one and.
Why should be our maximum expected future reward, and then we use that now?
Yeah, like optimal, and this max again is sort of saying if you take the optimal actions, kind of like under the optimal policy. Yeah, that's why I have a max here. So you can change this. Remember how we were saying we can change this instead of taking a max, you can have a policy pi. So then instead of having trying to search for, because this doing the max can take can be computationally demanding, you can just have a fixed policy. So then you don't have to do max. You just take what's the policy? The action would be just a pi of s. What's the policy when you're in a state s prime? Sorry, when you say s prime, it will tell you the action you have to take. So you can do that as well. And this was the way how AlphaGo was trained and AlphaZero, and how it won. It learned, first of all, so how it first learned to play games, even before it started to learn to play Go. It was trained to play here. So if you look here, it was trained to play Atari games. Are you any of you familiar with that? Have you seen? Okay. They had like a simulator of these old games, old Atari games, and basically these are games that were people playing in the 80s, and they were actually quite fun. Like, you can have like all these kind of games, like, the Pong game and like some other ones, and basically Pong is the one where you have like those two bars that kind of go up and down, and then you have like a ball in between, and you have to like make sure the ball doesn't reach the end of the screen, kind of, and you have to like, So it's a very simple game. It's a very simple game, but the key thing is that the network was only reading the pixels. The only input to the network was the entire screen with the pixels, and it was such an old game. It had like a very low resolution. It only had like a few hundred pixels, like 300 or 400 pixels. So 300 inputs in the network. And then they do convolutions, over them. They process just the pixels, nothing more. There was nothing else. It didn't know, for example, it was printed in a corner of the screen. It was printed a score, for example, but it didn't know that's the score. It had to like figure it out by itself that those pixels represent the score. So they were doing a lot of this processing of these images, and then with convolutions and so on, and fully connected layers, and the output was to predict the action. What action, given that frame, what action do you take? Do you go up, down, left, right, like the joystick actions, like you see all of these? And that was the optimization task. And what was fascinating again was that how the network was able to learn this by just having the pixel information, nothing else, just having the pixels as information. And then they were able to learn. The same model was able to learn, for example, to play like around 40, 50 games. The same model. So you just trained with different games, and it was learning how to process those pixels and how to like take the optimal actions without knowing what the game was about. It had to figure it out over the learning process. So very, very powerful technique, very generalizable. The same model could play 50 games and win at them. And at the same time, that model could also play, for example, then chess, then Go, all kinds of things. And the reason why it was very fascinating was also because, and let me see how much time I have so I don't go too much. Yeah, it was fascinating was because sometimes we humans create some models that are suboptimal. For example, for chess, you know how in chess there was this belief that, for example, a pawn is worth 1 point, yes. A bishop is worth 3 points, a horse is worth 3 points, and so on. Well, it turned out that it's much more complex than that, because it depends where the pieces are on the board, yes. Where they are on the board. A horse is much more valuable if it's in the center of the board than if it's on the edge, on the periphery. Or a pawn, yes, on the pole. Yes, So this point system is just an approximation, actually, and it's not. It's actually it could be the wrong model sometimes. In particular, what the model was learning to do is that it was willing to sacrifice the queen, for example, for winning the game. But otherwise, it was sacrificing a queen and then winning the game some moves later, for example. But according to the point system, that is bad, because if you sacrifice the queen, you would lose a lot, right? You lose a lot of points. But the model was doing that, and then it was trapping the king in a particular corner, and yeah, it's sort of like even checkmate. So these kinds of so it shows a bit how our systems were not actually fully optimal for these particular games. So
wait, I have a question.
Yeah.
About the big question about the chess. Follow to that one. So I like how you said about the chess, about the deep question learning. I just really know about like how the deep learning just do easy, medium, hard, or call adaptive difficulty.
Yeah.
So let's say that you play chess against your opponent. They just pretty much trying to learn your moves, and then you beat your opponent.
Yeah.
They get more and more harder over time, aka progressive difficulty. How they use deep question learning to do that? Since I'm like a chess player.
Yeah. So one thing that you can do again is you can have two models play against each other.
Mm-hmm.
This is what I was saying earlier, and they both imagine like two kids playing chess initially. So they're not both that good, but they can learn. They can learn in tandem with one another how to get better and better. If you ask a kid to play against a chess champion, it won't be able to learn that well, because it will lose right away. But if it plays against a player of its own kind of similar skill, it could make a lot of progress and learn better this way.
Let's see. By using that thing.
That's so here they didn't have to, because here they had a. They had a signal. So well, sometimes you don't. It depends. Sometimes you have to do that. Sometimes not. Like if you play a Mario game and you end up dying if you make a wrong move, that's a good reward signal. That's a good enough reward signal. And that's a single player game. So in some sense, you don't play against another player. It's like you play against the game itself. So you have to survive. You can do all these things anyway. So it is possible to as many strategies. Let me see. Shall we take a quick break, and then I'll have some concluding remarks. And actually, I think it'll be kind of interesting. I'll speak a bit about unsolved problems yet in AI, and kind of like how and what we haven't touched in the course, and what you could all do next. So let's take a 5-minute break, and we also have like an announcement our colleague wanted to make. So
Bargaining update.
Do you want to come here so people
I
on
do have
Zoom?
The letter ready. I have the letter regarding about the bargaining update. I have the bargaining update right now, so I'm trying to find it. There we go. There's a bargaining update from last night.
So come here. So okay, so we have an update. Go ahead.
I need to put the screen. Like
You want to put the screen here?
And then just to share the
Okay.
thing.
Oh, well, do you have an HDMI?
Yes, I do. It's gonna block out in 2 seconds. Okay, I want to see my screen.
Oh,
I had to go to Zoom.
have to go to Zoom.
Yeah, I forgot. I really forgot about that. My bad. I wasn't prepared. Zoom error. Hello.
So we'll have a short announcement from our colleague, but then we'll resume quickly afterwards.
Yeah, I can share the update. You
Go ahead.
disable square screen.
Yes, let me ask. Go ahead.
So there. I kind of don't know where is it. I kind of like don't know where is the screen sharing. Maybe looking for it for a while. I think it's this one. There we go.
Okay.
So this is the one that we are doing right here. So on last night, the SR and our bargaining team, they voted to adopt a resolution to the UC administration that offers the following major concussions, which means they gave up their demands on the following four points. the job are demands for disabled workers to receive access need without having to provide medical documentation. The reason why is one of our demands, because once you provide the medical documentation, the UC does never give any accommodation. And I hear a lot of testimonies from one of the caucus meetings that our bargaining team refused to listen, and they pretty much vote on the 10-9, 1 to abstain. Our bargaining team has voted against to drop, but the 10 votes has gone in. So that's another one. They also draw the dependent healthcare.
Hey, I think you're muted.
Oh, sorry. Let me say this, sorry about that. So on the night of November the 30th, members of the SRs and the members of the collective bargaining team voted to adopt this resolution for the UC. The first one. Yeah. So the first bullet point, I'm going to explain this four bullet point right now. What I mean, I'm going to explain the first one so I'll be muted. So I'm going to say, so you guys drop our demand for disabled workers. I made a speech regarding to defend it, but of course they don't listen to the rank and file members, aka the union, so they drop it. Second one, they drop dependent healthcare coverage completely. They drop the child care summer seats completely from 6K to 3K, and they drop our wage from 54K to 43K a year, and they drop our call at demand from the same thing, 10 to 9, on dropping those things to abstain. So perhaps the most shocking was the rationale for that decision to adopt the 43 wages demand was moved to 42 as a friendly amendment from the UC. And there's a link over here as a way to consider. I'll send this one as an email later today. This move comes in the third week of our strike, during which the UC has made no serious concussion or compromise towards us. 24 hours before this move, the UC presented a race article to a 2865 identical to the pre-strike November the 9th of 2018 package. This move only offers for 1.5% for SRU, which means the students' research. Since the strike begun, there has been no serious offers for the UC on wages, childcare, or NRST that comes even close to the pre-strike UAW proposal. So all representatives for our bargaining team, especially the Cruz, we vote against SDSRS from Santa Barbara, Merced, and Riverside, as well as one representative from San Diego, and one as our representative for UCLA. Because there are two, there's one of them vote against from UCSD, and there's one that vote against us from UCLA from last night. All alternative moves that suggest during the bargaining team meeting during including 40,000 ministries compromise.
It seems he's mute on Zoom.
Voted down in a way because they don't really listen to us.
People on Zoom can't
I'll
hear
tell
you.
you about more about my insights because I just witnessed it the last night's meeting. So last night's meeting, I went to the caucus meeting and there were they pretty much give like a 30-second because there were a lot of people doing it. There were a lot of people gave angry comments about like how in the world you guys rush to compromise so fast, so as to end the strike with nothing to gain during this historic strike moment. We've been trying to stress that like why you guys are rushing on this movement for so long, but our bargaining team refused to listen. So the following actions that we are taking as of now as the rank and file members, as a part of the department head, steward, or representative for the computer science department, is that I'm going to mobilize try to help you guys to understand the strikes that we need you guys to go on strike this week as soon as possible. So put as much pressure to the UC that we are serious about it. We have the lowest turnout for computer science history since the early days of the strike already. So I'm just asking you guys to join the rally tomorrow at the main picket line, where I'm the one that's going to host the department town hall meeting to discuss everything what is going on. There are now calls for like certain recalls process in certain UC universities like UCLA and somewhere else, I believe, that who they abuse their powers by pretty much shut everyone off. So instead of doing an open caucus, they just shut everyone off. Because there were about
1,000 1,000 people show up to the Zoom meeting. There's the first one that's called the regular Zoom. 500 come to the Zoom meeting to discuss about why you guys are dropping. So there was an overflow, which about additional about like 200 more going to the overflow to show that we really care about the quality demands. So, right, the following actions that I'm taking as a department steward for the computer science is to pretty much for this class, 2 of our readers has officially gone on strike. So they're not going to grade our assignments. So I really congratulate them for staying up for our demands and participate in our strike by refusing to grade our assignments. Our facility member, our professor over here, has really endorsed our strike. So we're trying to talk to my professor on how we can coordinate this out. I'm writing a facility support letter because physics department has already wrote a letter of support and condemned the office of the president and their bargaining team for obstructing the bargaining process for 3 weeks during the strike. There are about 30 unfair labor practices being filed already to the Public State Relations Board. 6 of them have already been charged to the UC, so there'll be a hearing about it. That say that they're being obstructing the negotiation process for so long, aka shallowboggling, which means they pretend to do it. Anyway, that's it for the announcement for today, and I hope you guys join my rally at 1 p.m. to so I can talk to you guys more about this, how we can move forward together as a department. I want to make sure that I will send all these letters and updates later today. Thank you for your time.
Okay. So we're resuming shortly, 1 sec. Can you all hear? Are we connected? Can you hear on Zoom? Yeah, okay, great. Oh.
Yours is Apple, mine's PC.
That's okay. That's okay. All right. So just I didn't have too much. Just a few concluding remarks, more let's say philosophical and even I wanted to first highlight a few things we haven't touched in the course, and you could touch later on by taking more courses. So in particular, for how many of you this was the first ML class? Was this the first ML class? Okay, and some of you have taken, so I suppose you have taken more than just one. So in general, for example, ML is such a comprehensive topic. It takes a long time to really understand these techniques. So for example, when I was in undergrad, I remember I took around 2 or 3 ML classes, and I took another 2 more in grad school. So it's quite a lot, and I'm still not there's still many areas of ML that I don't I'm not that good at, and essentially what I'm trying to say is that there's a lot to do. There's a lot to cover and to learn. And for example, things that we haven't covered are, for example, Bayesian networks. We haven't covered how do we do inference in these arbitrary graphs, for example, and how do we do this? There's a lot of algorithms. For example, the sum product. Gosh, I forgot the names of exactly, but they basically pass messages across each other and message passing. Sorry. No, that's different. That's also like those are graph neural networks are networks that are neural networks that run on graphs. This is Bayesian networks are basically where you have a graph of representation. There's representations, but where you predict. Like for example, with the case of the Asia network, we had like try to predict like if somebody had a particular I forgot a particular medical condition given some an X-ray scan and some like travel and for example and so on. So these are the kinds of like Bayesian networks that we haven't covered. There's also numerical optimization methods, for example, that momentum type of method that we haven't covered. For example, Adam is a very popular optimizer, which is momentum. So it's a stochastic gradient descent, but also uses momentum inertia basically, and that's something we haven't covered. We haven't covered variational inference. How do we learn solutions? How do we learn not just a single solution, but a whole distribution of solutions? And this is what variational inference is about, and this is something that is very important for some tasks. Like for example, for the image reconstruction task we're talking about, the 2D to 3D reconstruction, there's multiple. For a single, I was giving an example for a single brain slice. There's multiple 3D reconstructions that could be all good solutions, and we have to use variational inference to infer those. We haven't touched on too much on distributional losses. Again, the KL divergence, Wasserstein distance, and so on. We haven't done any meta-learning at all. And meta-learning is this concept of learning to learn. How do you learn some tasks and then have the ability to generalize to new tasks that are quite similar? Like for example, if you let's say if you do some kind of image processing task, so let's say if you do some kind of like image manipulation, landmark detection in images, image segmentation, and so on, how do you generalize to some new task? Like for example, how do you infer depth, for example, like you want to do these.
With you mentioned earlier with the teaching the model Pong, I was able to do like 40 to 50.
That'll be that's a good example, exactly. Like in some sense, how you learn some games and then try to learn to play a new game, for example, that you haven't seen before.
What meta learning went on.
Yes. And there's many examples. Like even I suppose even in a reinforcement learning, like a robot learns to navigate indoors, and then it learns to navigate in some other tasks, like for example on outside on the streets, and then the new task, the meta-learn task, is how do you navigate on sand, for example, like kind of like by having learned to navigate in these other similar environments. But then sand, for example, is much more difficult terrain to like kind of like it's you can get stuck and so on, like in the wheels. So this is another all kinds of examples like that. We haven't talked about causality at all. Like for example, like sometimes this can be very important because sometimes we're interested in the causes of which variables caused a particular prediction and which ones didn't. For example, and this is very important in medicine, for example, because you're trying to find, for example, you have a data set of millions of genes, and you have and try to predict a disease, and you're trying to find what are the genes that are causing that disease. For example, all those like millions of genes you have. So causality is very important for some particular applications, like medicine. We haven't spoken about quantum machine learning at all, and how there's been some theoretical and so these are all like potential kind of future directions. And this has been a lot of theoretical work recently on how to build. How would you do the machine learning on a quantum computers, where you don't have where you have completely different. You have qubits, you have completely different properties of entanglement and so on, and how do you do machine learning on those kind of architectures. But anyway, if you want to study some of these topics, you can take CSE 290, which I'll teach in spring. So this is an advanced seminar in ML, and when some of those stuff, for example, we could touch on by reading papers, by having discussions. So this is a seminar class, and you could take that, for example, if you're interested in more of these topics. some key applications. Let's not forget. So again, computer vision and computer graphics is some really key applications in machine learning. So we haven't discussed too much about that. Again, we more spoke theoretically about machine learning. There's a lot of stuff that is going on. For example, if you want to do image segmentation. So again, you have an image of a busy street, and you're trying to find out which ones are people here. You put these bounding boxes, you tag them. Is this a person? This is a backpack. This is a car, and so on. And you do segmentation, so you do the contours, which are very important. It is like you tag each pixel that belongs to this car object, like that. This is a very, very important task, image segmentation, and it's also done a lot in medicine. We try to segment the actual regions in the brain, for example, the hippocampal region. You tag those pixels, and then you measure the hippocampus to track a particular disease over time. Image registration or alignment is a very fundamental task. How do you have two images, like two brain images here, and you have to align them so they match? And it could be of different modalities. For example, one is an MRI scan, one is a PET scan of the same person. The same brain from the same person, just different types of images, and you have to align them to do a study on that. And it's a hard problem. It's not an easy problem, especially when you have deformable objects or soft tissue or that kind of stuff. It's not easy when you have non-rigid objects. 3D reconstruction, again, we hinted about that. You have a 3D object, you have multiple screenshots from different angles, like multiple 2D pictures. How do you reconstruct the 3D shape from a series of 2D snapshots of this image? And for example, again, this is of 3D reconstruction for terrains, for the whole terrain. So all kinds of applications. There's applications in natural language processing. For example, where we again have an image and we want to caption it. Like how do we're given these images, a cute dog sitting in a hadron and so on a beach. And we have a training set, and then we learn how to caption new images. Then we're given a new image that could be, let's say, similar, and then it gets automatically captioned by the machine learning model. But anyway, for any of these, so there's courses that we offer in the department. So we can take CSE 264, 260, computer vision, computer graphics, or the natural language processing course, which is 244B. If you want to see more of these applications, on these kind of applications of how ML is used in these settings.
To take 244B, you have to take 244A, right?
That's probably right. I haven't. Yes, that's probably right. Yeah. I'm not that familiar with the prerequisites, so I think you know better. So I wanted to spend the last maybe 10 minutes. So how was the course? Did you like it? Did you sort of like?
Yeah, really enjoyed the course.
Yeah.
Yeah. Even though there's a strike going on.
Yeah.
The strike didn't help with
Yeah.
course,
So I hope so please also leave some feedback, and leave feedback at the end of the course. To do written feedback. I'd really appreciate it if you leave me as much feedback as you can, constructive, so I can improve the course for the future generation of students that come afterwards. So because I'd really like to improve it. So it was my first time teaching it as well.
Okay,
So
yeah, I just want to focus more of a concrete example that is like similar to our homework, so then we don't feel like go to online research to figure what's going on. I just feel like we just need more like a concrete example of what we're doing, like hands in class, and then we do our home, and then to like pretty much to help us prepare for our homework assignment, instead of like go to this conceptual and just make me be like, what is going on here?
Yeah.
That's like my only like feedback.
Mm-hmm.
To the course.
But right in the what I'm trying to say, leave me written feedback on Canvas, and I'll try to improve the course for the next students that take in next year. But anyway, in general, like I'm really proud of you. I'm really happy with what we've done so far. I'm really proud of you all, and I think because I want all of you to sort of at least like come out of this course and really feel like you've learned some really core components of machine learning, some critical, let's say, fundamental concepts. You can work with them. Yeah, I didn't want you to memorize that much, but rather really work with the concepts. And And I hope, like maybe some of you will end up, working in industry on like, as a machine learning scientist or work in academia somewhere. But I hope, some of this stuff could come useful. Who knows, maybe in some years later. I wanted to end maybe in the last 10 minutes. I wanted to talk, if you would like, some open problems in AI, like what hasn't been solved, sure. And maybe you will be the next generation of scientists to solve them. So there's several things. So many things we haven't yet solved in AI. For example, text understanding. It's actually like it's still we've made so much progress. And it was actually funny because as I was putting the slides last night, I saw that OpenAI released a new ChatGPT, a new AI model for text understanding that is quite powerful. So maybe I have to refine these kind of like slides. But in general, the key thing is that sometimes we can generate a lot of text, even a lot of essays and stuff that seem to be quite coherent, like and in the flow, but for example, sometimes they don't have a good understanding of the world. It's like a common sense understanding. This is something I feel we're still lacking. For example, there was I don't know if you know about Gary Marcus, but he was like more like a philosopher that was playing around with GPT-3, I think some months ago. And for example, he gave an example, something like you put in some text. You imagine someone writes some text, and then you put like, you're making a cup. You have a mug. You pour some hot water. You add some mint leaves. You add something else, a bit of milk, 2 more ingredients, and then you drink it. That was the text. And then the model had to autocomplete what would happen next. And the model would say something like, "Oh, you are dead now. You are dead. You are like and it kind of like and it went on to like on a story of like how you're dead and you like whatever, I forgot the whole details, but you're like leaving your body and you're going like you're floating and so on. But the whole thing, you can say like the model is lacking a common understanding is that you won't die from putting hot water and some mint leaves and some milk in that. Like you won't die from that. It was lacking this kind of understanding. But it saw some correlations in some previous texts of how some people were doing that and they were drank and then they died. So it autocomplete like that. But it's clearly lacking a bit, and we don't yet know how to. It is more high-level reasoning how to deal with it yet. And I wouldn't be surprised if similar things are still happening even with the current AI models. Some complex computer vision tasks we still haven't solved. For example, how many of you are familiar with object permanence? Okay. So object permanence is a task that, for example, is not solved in computer, and that is not solved. And what object permanence means is that it's not. When babies, for example, you play the peekaboo, sort of like you hide you're playing with a baby, you hide your face behind your palms, and then you say peekaboo, and then peekaboo, and they're always surprised because you disappear and then you reappear. So
stop existing when they don't.
You stop existing basically if you don't see the person. They don't realize that you are behind your palm. Your face is behind your palms. You're behind the screen. So this is something that nowadays the computer vision models still don't have, and the people are trying. Actually, it's an active area of research right now. If an object goes behind a wall and reappears afterwards, the model doesn't have an understanding that it's actually kind of moving behind the wall and it still exists.
Self-driving vehicles a lot. Like they'll see a pedestrian maybe walking towards the street, and then they'll disappear behind a parked car, and then they'll adjust his path like they're not there, and then the person will reappear on the same trajectory. Exactly. So that's a very good example. So for those on Zoom, our colleague was saying how if you have the same thing happens in self-driving cars when you have a pedestrian that is coming behind a car, and then essentially once the person disappears behind the car, it's not seen by the computer vision model. The computer vision model thinks it doesn't exist, and then the person somehow suddenly reappears. So let me say something. So babies learn this when they are 7 months old.
babies learn object permanence when they're 7 to 8 months old. So they don't have it until that age. So this is telling us a bit about how, how much more we still have to make, So, and who knows what other kinds of and there's many other things we haven't solved, for example, and even that babies acquire much later. Visual navigation around the world. So that's still a big problem. So we don't have self-driving cars yet. We don't have robots going around. That's not solved. There's so many problems still. Learning interaction is another kind of type of problem that we have. And what I mean by that is because sometimes the interaction of a robot with the environment is way too rudimentary still. And it doesn't, for example, we have robots that cannot easily explore streets without getting stuck or hit by a car. We have these kinds of settings. Or sometimes, so you want to have a robot let it explore, let it work, but it gets stuck all the time, for example, and it needs a lot of help from humans to be able to get unstuck and so on. So or dialogue systems that are not good enough to keep people interested. So what I mean is, for example, you want to have some people to interact with the agent for the agent to be able to learn, but if people aren't interested to speak to the agent, then it won't be able to improve. I have a question there. Oh wow. Oh, so I should probably again refine that. Yeah. No. That's a good point. So.
Because it could call and schedule an appointment for you, and the person on the other end couldn't tell if it's happening.
Right. Oh wow.
Well, there's a lot of generators that can do that, though.
Yeah, so
I remember I interacted with the Amazon Alexa 2 years ago, and I could still tell, of course, it wasn't. It wasn't passing the Turing test, at least. I could tell.
I think
Google Assistant. Got it.
They're never but more about robot interaction along the dialogue systems. Really interesting.
Yeah. And there's a few more things. For example, mathematical proofs. We still haven't. The current AI systems are currently at the level of a 9th grader, from what I've read. So we still we have some way to go on that. Robotic manipulation tasks. For example, the current robots with the robotic arms can do some basic things like grab objects, move them, grab an object from here and move it there, or even dropping like that. But they cannot do more complex tasks that involve a series of actions, for example, cooking a dish, cooking an omelette, making that it's quite a complex task. You have to open the fridge, you have to take the eggs, put them on the counter, and so on. Take the pan, pour oil. It's too many tasks, and the robot gets stuck and doesn't manage to cook even an omelette. So these basic things we don't have at the end. So robotic manipulation, and so on. Writing computer programs and high-level tasks. We could have AI systems write computer programs themselves, like an algorithm that, does all kinds of things. And and I think we're actually getting there in some sense, but still we don't have, we don't have that. Energy efficiency is another big problem. So our brain consumes way less energy than the bigger supercomputers nowadays. For example, the biggest supercomputer in the Netherlands in 2021 was consuming 50,000 times more energy than a human brain, and it wasn't able to do all of those tasks that we can do still. So we still have to work a lot on that front. And I'll just end this by telling you so what are the schools of thought of how we can achieve this? Currently, I would say maybe a few 2, 3, let's say, schools of thought of how we can achieve artificial general intelligence that researchers currently believe in. And one of them is this idea of scale. So and we scale the solution. So and this has been the main school of thought in the last decade. So we scale by having bigger data and bigger networks. So basically, we increase the trained data sets to millions, billions of images. We increase the number of parameters to billions and so on. So say, for example, the number of parameters in GPT-3 is around 175. I just Googled this last night. And it's huge number of parameters, a huge model. So this has been one approach. People believe that if we can scale these models, make them bigger and bigger and bigger, we can achieve intelligence. This is a school of thought. This is, but it's not the only. And this has been the mainstream against strategy since 2012, I would say. But it's not the only one. Maybe that's not enough. It might not be enough, for example, to achieve intelligence. It might be more than just scale that we need. Another school of thought is to imitate the brain, followed by other kinds of people. So here the idea is that nature has already found a solution to intelligence. We already have, it's in our human brains or in the brains of other animals and so on. And all we have to do in that case is just to imitate that. We don't have to create new kinds of ways of intelligence and so on. We can just follow exactly what the brain does. And there's another school of thought that is followed by some people, and they're trying to make these neural networks that imitate the human brain as much as possible. And we just have to follow that path. And there's again counter arguments to that. For example, one good one is, for example, of how planes evolve. Initially, when people were trying to, in early 20th century, when they were trying to make airplanes, they were trying to imitate birds, for example, and try to make airplanes with flapping wings. But we ended up having fixed wings instead of kind of flapping wings and so on. So we didn't follow exactly nature's path in achieving flight. And we don't know. We don't know. Maybe there's better ways, for example, to solve some tasks than how the brain does it. But anyway, this is how some people approach this. And spiking neural networks is a great example of that, where you have these neural networks that model how neurons work much more accurately by modeling the action potentials of these neurons. And finally, the last school of thought I wanted to mention about is the idea of embodiment, is having a body, giving the agent have a body. So look at this video, for example. Look at this little child that is playing around in sand. It has some toys. It's it decides what to grab, how to pour sand and so on. And then grabs another toy. Again, does all of these things. The reason why I'm showing is because sometimes this is how kids learn by constantly interacting with the environment. They constantly interact with the environment. They decide to grab a new thing. They take a new action. They start to stand up and then go somewhere else to a different set of toys and so on. They constantly interact with the environment. They play, and that's how they learn. But for that you need to have a body. You need to have the ML model cannot exist just in a computer. It needs to be, let's say, deployed in a robot. So the idea would be you deploy it in a robot, for example here, and you let the robot explore on the streets, for example, to try to learn, take actions, decide what kind of data to acquire, what to do, where to explore, and so on. And it's how you can build a model of the world, understand a model of reasoning about the world.
I saw something kind of similar to that. I don't remember where it was, but it was this robot in a mall, and there was this tendency, especially for children, to come and harass it and tempt it. And so it learned, I don't know what the training algorithms they ran on it, but it learned to kind of recognize children and kind of detect their path behavior. And if it seemed like they were coming to mess with the robot, it had learned to do things like stay near their parents.
Oh, wow.
Less likely to trap the robot.
That's fascinating. That's fascinating.
Yeah, so it would I thought that was really interesting. It's right if it stays near an adult, less likely for children to abuse it.
Yeah.
So I had learned some tricks like that to get out of these situations where it would get trapped and stuck intentionally by kids.
So for those on Zoom, our colleague was saying how there was this example of a robot that was it was in a shopping mall, and it was being tripped by kids. So the kids were bullying the robot, and the robot was learned how to some interesting behaviors, like how to always hang around next to the parents of the kids, because this way it wouldn't be. So that's super interesting. Yeah. If you send me a link to that, send me a link if you find it. Yeah, send me an email. But this is anyway. So I want to say this is another school of thought, and this is for people who also work with robotics, giving the model a body and letting it learn more. Learning is a constant process. It doesn't just stop at a particular point, like how we do in the current ML paradigm, where we train from many iterations and then we stop. It's constantly the world is constantly changing, and we have to constantly learn to adapt to the world. And that's the end. So I hope you enjoy the class, and thank you. And yeah, and do some machine learning. Yeah.
Thank you.
You're welcome.
You're still holding your usual office hours?
I'm still holding office hours today.